Hi everyone. In experiment 1 of this quantitative analysis course, we're going to first look at several different fundamental techniques that will help you to be successful as you move throughout this course. And one of the first things that we're going to look at is the difference between accuracy and precision. And specifically in this experiment, we're going to look at the accuracy and precision of several different measuring devices, which of course is very important for a quantitative analysis course. We're actually trying to figure out, concentrations or pHs or things like this as you move throughout the course. So before we do that, let's talk a little bit about what is accuracy and what is precision. So when we look at accurate values, as you may recall, we're looking at close to the bullseye. So values that are close to the accepted value are considered to be accurate. Precise values aren't necessarily accurate. So we can see these values here are precise because they're close to one another, which is what precision is, but they're not close to the actual bullseye. And this happens largely for two major reasons why you'd have precision and no accuracy. One of the major reasons is that the values are coming from some kind of systematic error. So there's some consistent error, like say the balance wasn't calibrated properly, for example, so everything's a gram less than it should be. That's just one example. Or it could mean that the actual bullseye is over here. In this course, it's more common that there's some kind of systematic error. And then of course it's not shown here, but you could just have random values that are neither accurate nor precise, like one here, one here, one here, one here. And so that's basically that. So to review, accuracy is values close to the accepted value. And precision are values that are close to each other. Values, of course, can be both accurate and precise if they're both close to the accepted value and relatively close to one another. Now, in science or math, we can actually do some calculations regarding accuracy and precision. And the most common precision calculation is standard deviation. And here is the formula from standard deviation. For standard deviation. Standard deviation is kind of like the average deviation from the average. So it's looking at how far away is each individual data point from the average value and then averaging all of those values. That's not exactly what it is, as you can see from this formula here, but that's pretty close to what it is. And it has the same unit as the measure value. So if you're measuring milliliters, the standard deviation's in milliliters. If you're measuring grams, the standard deviation's in grams, so on and so forth. One fortunate thing is we're not going to be doing this calculation by hand pretty much ever again. We're going to use Excel to do this calculation, and in just a little bit in this video, Tim will show how that is done. Then we use something called relative standard deviation, RSD. I should probably have written out here, relative standard deviation. And this has values of parts per thousand because we multiply it by 1,000. The RSD is the standard deviation divided by the average times 1,000. And again, it has units of parts per thousand. So relative standard deviation is good if you're trying to measure values on different scales. So for example, the deviation in the mass of a car in grams from one car to another car might be relatively high because a car is heavy and the standard deviation in grams might be very high. But if you look at a single ball bearing in that car, which maybe has a mass of 0.25 grams, if the standard deviation were a whole gram, that would be a big problem. So relative standard deviation is a way for us to normalize these values and kind of look at them relative to one another. We do it in parts per thousand instead of a percentage. If we multiply by 100, it would be a percentage. But these are common calculations. And again, Tim will demonstrate them using Excel shortly. Finally, accuracy calculations. So precision, again, is how close the values are to one another. Accuracy is how close they are to the accepted value. So one way to calculate accuracy is percent error, which is the absolute value of the experimental value minus the theoretical value divided by the theoretical value times 100. Because it's a percentage, we multiply by 100. So essentially what we're looking at is how different is the experimental value, or the average experimental value is usually what we use, from the theoretical value. And because we want it as a percentage, not as just a difference, we divide by the theoretical value and multiply by 100. So this is the difference between accuracy and precision, and also the ways that these things are calculated. Now that we've talked about these things generally, let's look at what we're actually going to do in the first part of this experiment. And to do that, I just want to bring up the camera. So what you're going to do is you're going to use 3 different types of common measuring devices in chemistry labs. And maybe you've used these types of pipetters before, and maybe you haven't, but these are basically the VWR's version of an Eppendorf pipette. And here we have one that will measure from 0.1 milliliters to 1 milliliter. We also have one that will measure from 1 milliliter to 5 milliliters, and these are the common volumes you're going to use in this course. And then we also have a volumetric flask, which if you took general chemistry here, or probably most other places, you've used before, and this flask has one job in the world to measure 25 milliliters. So we're going to look at the accuracy and the precision of these devices. We'll look at accuracy by looking at, in the case of the 0.1 to 1 milliliter pipette, we're going to see if we can deliver half of a milliliter from one place to another. So we're going to look at the accuracy by comparing the average amount transferred to the accepted value of half of a milliliter. And then we're going to look at the precision by doing this 5 times and looking at, is it reproducible? Is it delivering half a milliliter or whatever volume it's delivering over and over and over again? And we're going to repeat that for both for the other pipetter and for the volumetric flask. Now that you have a basic idea of what's going on in this experiment and what we're trying to figure out, we're going to switch gears and look at what do you do with the data once you get it. Because actually getting the data here is relatively straightforward. You're just going to measure some masses and convert them into volumes. Let's look at what that data looks like next.
So, now that you have an idea of what you're going to be doing in the lab, I'm going to take a couple of minutes to discuss making your Excel spreadsheet for the first part of the experiment. So, when you're doing these experiments in this course, it's really important to have a well-organized Excel sheet because your TA is going to need to be able to interpret what you've done in order to give you the credit you deserve. So here you can see I've got a lot of data on this sheet, but it's pretty well organized, right? Everything has labels, there are units involved in each of my measurements, and everything is well outlined and clear about what I'm going to be doing. Up here is my small pipette data, then my large pipette data, and finally my volumetric flask data. So when you're setting up your Excel spreadsheet, I would recommend you set one up that looks very, very similar or even exactly like this one so that your TA can know exactly where your data is and how to find what they're looking for. So I've already gone ahead and entered in my water temperature. This is roughly room temperature water, and I looked up on the chart given to you in the lab manual the density of water at that temperature. So in this case my temperature is 21 degrees Celsius and my density at that temperature is 0.9980 grams per cubic centimeter or grams per milliliter. I've also gone ahead and entered in my mass of water in the beaker for each of the trials using my small pipette data. You'll notice that I added approximately 0.75 grams of water or milliliters of water per transfer rather than the 0.5 that you're supposed to do in the experiment. So keep that in mind when you're looking at my data. So what I need to do now is I need to figure out the mass of water that was transferred in each of the trials. So to do that, in Excel, you may be familiar with it, but I'm going to go through how to use it as though you weren't. So in Excel, in order to do any calculations or any sort of formulas, you need to start by hitting the equals key. Once you have the equals key, that lets Excel know that what you're about to enter is going to be some kind of math or some kind of calculation. So in this case, in order to figure out the mass of water transferred, I need to take the current mass of water and subtract out the mass of water that was in it before my most recent transfer. So in this case, it's the 0.7478 minus 0, which of course is going to be 0.7478 grams. Now for each of my trials, all I need to do is hover over the bottom corner of that cell in Excel until it turns into this little 2 black arrows and drag down. And now Excel will copy that formula down into each of the additional cells. And you'll see that because I haven't done anything but tell it cell to the left minus the cell above that it's carried forward each of the calculations so that each measurement is subtracting the mass from the measurement before it, which is what we want because we only want the individual measurements. Now I need to calculate the volume of the water transferred. Well, since density is equal to mass divided by volume, we can rearrange that formula so that volume is equal to mass divided by density. So to calculate the volume, we're going to do exactly that. We're going to take the mass of the water that we transferred, and we're going to divide by the density of the water at this temperature. Now this time, if I hit enter, it'll give me a lot of sig figs. We'll deal with those in a second. And it'll give me a volume of water transferred. Now I'm going to start by dragging this down just a couple of cells so that you see a problem. It's going to say that it can't divide by 0. And the reason for that is if I go into this, you'll see that it's still taking my mass of water, but it's dividing by this empty cell up here instead of by my density. So to fix that, what we do in Excel is anytime we want one number to stay the same as we drag it down, we need to hit F4 on that number. And it'll add these little dollar signs, which tells Excel that that cell in particular stays the same. So now as I drag it down, the blue number, the C10, will change, but the B5 will stay the same every time, so it'll always reference that density. So now if I drag it down, you'll see that we get numbers for everything. Now, of course, we don't have this many sig figs, so we're going to change that by coming up here to the number, and we're going to decrease decimal is the function in Excel, which will show fewer decimal places, and we'll go down to 4 decimal points, which is what we can measure using the balances in our lab. Next, we need to calculate our values that Colin went over with you at the beginning of the video. We need to find the average, the standard deviation, the RSD, and the percent error. To calculate average and these various things in Excel, there are functions built into Excel. We could add all the values, then divide by the number of values, but that would take a while. So instead, what I'm going to do is I'm going to use the function present in Excel called average, which you saw pop up below it. So if I type average and then open parentheses, I can select by clicking and dragging all of my data, close the parentheses, hit enter, and it'll immediately calculate my average. I could do the same thing for standard deviation, but in Excel, standard deviation is STDEV. You'll notice that for some functions it's the full word like average, and some it's not. In the case of standard deviation, it is STDEV, but when you start to highlight it, you can double click it and it'll enter in the rest of it for you, and again, highlight all of your data, close the parentheses, and hit enter. So now we have an average and a standard deviation. To calculate RSD, we're going to select our standard deviation, we're going to divide it by our average, and we're going to multiply by 1000. And it'll calculate our RSD. The last thing we need to do is calculate our percent error. If you'll remember, percent error is the absolute value of the accepted value minus the measured value divided by the accepted value times 100. So I need to have the absolute value function in Excel. To do that, it's ABS. You'll see it says returns the absolute value of a number without its sign, which is just the definition of absolute value. So we're going to use the absolute value, and we're going to take our accepted value, which in this case, I was transferring 0.75 grams or milliliters of water. So I'm going to do 0.75, and I'm going to subtract out my average because I don't want to check the percent error for a single value. I want to check the percent error over the array of my values. So I'll subtract out my average value. I'll divide by the accepted value, 0.75 again, and multiply by 100. And find that we have a percent error, a very low percent error of 0.265% or so. Now, I want to point out one thing that could happen during your experiment. During your experiment, you'll notice that each of these numbers is going up for you by about 0.5 and for me by about 0.75. But it's very easy to make a mistake when working with a pipette or in lab when you're talking to your lab partner and you forget what's going on. So let's say during the course of the experiment I look down and this number, rather than 3.0123, is more like 4.526. Now, or 5260 rather. Now, I can see straight away that this number is way too big, right? I have clearly added more than 0.75 milliliters of water. So if during the experiment you notice an obvious error like that, it's really in your best interest to stop what you're doing and address that immediately. If you wait until after the experiment and don't look at your data or try to see if there's any obvious errors until after you're done with everything, there's a good chance that you've already gotten rid of your solutions or you've diluted that solution beyond the point where you can use it again. So it's best to be looking for these things while you do them. So in this case, if I were to notice that, the fix would be very, very simple. I would simply empty out all the water from my beaker, tear it again at its new 0 volume, and add another aliquot of water. So this number would again be roughly a 0.75 value, because I would be referencing back to my 0 rather than the 2.25, because we can't just remove the volume of water we added, so it's easiest if we just dump it out and start again. But that's just something to keep in mind while you're doing your experiments. You'll notice that for the 1000 to 5000 values, that we already have everything added in for this. We've already done all of the values for the larger pipette and the volumetric flask, and you'll notice all of the averages and standard deviations are calculated. Interestingly, it's easy enough to do this by simply copying and pasting in Excel. To get all of these values, if you copy without Excel opening strange windows on you and paste, Excel automatically updates the formulas to reference the cells that it's near rather than trying to save the values. The only thing that it kept the same was this $ symbol that we did before, which ensures that we're still referencing the density. We can even do this for the average, standard deviation, RSD, and percent error. You'll notice that when I copy and paste, it changes briefly before it updates to my new values. So you can have all of these calculations ready to go ahead of time, and all you have to do is fill in your measured masses. One thing I should have pointed out earlier was that when you have a problem with your data point, so for instance when we had that number that was about 4 up here, when we restart the data and this number ends up being around 0.75 again, you'll notice that it messes up our numbers on the rest of these, right? We get a couple of negative numbers, we have a measured mass transferred of 3 grams, because this number would need to be updated to about 1.50, but you'll notice that these numbers turn negative, so we have to change the math. So in order to do that, we need to reselect what we're subtracting from. We still want to have our 0.75 grams from this trial, but we're now subtracting back from the 0 point that we started at, which will fix the rest of our numbers moving forward so that we don't have that error carrying forward. In the lab manual, and eventually you'll see in the guidelines and rubrics for the lab reports that you need to write for this course, it sometimes says things like comparing values, or it wants you to talk about your data, and it's important that you do those things where it asks you to, which is often in your results section of the experiment. So that will sometimes require you to write a couple of brief sentences of explanation in Excel. So for instance, if we wanted to talk about the percent error or the accuracy or precision of this experiment, we could type a brief sentence talking about the accuracy or precision in Excel with just typing into a cell next to the data. So you could type here, the experiment appears to be accurate because, and then finish the sentence. These don't need to be long, in-depth discussions, but it's important that when it asks for an explanation, that you do provide at least a sentence or two giving an explanation of what you're asked for in the guideline or the lab manual. So in this case, the experiment wants you to discuss the relative accuracies and precisions of your 3 different measuring devices. So here we could say that because the RSD for the small pipette is 2.8, the RSD for the large pipette is 15.7, and the RSD for the 25 milliliter volumetric flask is 10.8, that the small pipette is the most precise because it has the smallest RSD, and that the large pipette is the least precise because it has the highest RSD. We could also look at the percent error to talk about the accuracy of each of our 3 measurements, and in that case we'll see that the percent error of the small pipette is the lowest, making that the most accurate measurement, and in the case of the 25 milliliter volumetric flask, it has the largest percent error, making it the least accurate. These may not be the case for your measurements when you perform the experiment, but it is what happened with the values that I've decided to use for this video. So we can see from this experiment that even though one of these ways of measuring volume might be slightly more accurate or slightly more precise, it's important to note that the accuracy and precision is good in all cases for all of these measurement types. Said another way, what this means is that volumetric glassware or volumetric pipettes are a good way to make measurements in chemistry in order to accurately and precisely know exactly what volumes you're adding or transferring, which will come in handy a lot in the future when you need to make very specific concentration solutions throughout the rest of this course and your career as a chemist.
In part 2 of this experiment, we're going to explore calibration curves. If you took general chemistry here, or possibly anywhere else, you've seen a calibration curve before. A calibration curve allows us to measure, relate something that we can measure, in this case that's going to be conductivity, to something that's more challenging to measure, such as concentration of a solution. But if we can relate those two variables, so we know the mathematical relationship between them, if we can measure one, we can find the other. And in part 3, you'll actually be measuring the conductivity of a solution. But before we talk too much about conductivity and concentration, let's remind ourselves what happens when we dissolve ionic compounds in solution. So ionic compounds contain a metal and a nonmetal. In this case, you're going to be using NaCl, and our example is going to cover KBr. As you saw in the previous part of this video, we're not going to go over the exact equations, mathematical equations and things that you need to solve so that you could just copy from the video. We're going to just pick a different example. It's actually the example you're going to find in the lab manual. It's very similar, and we're going to go over that, so that way you still have to do the calculations and get the practice. So in this case, when we dissolve NaCl in water, we get sodium plus, it's a 1A metal, so it has a +1 charge, which is aqueous. Remember, aqueous means dissolved in water. And chloride, Cl minus, which is again aqueous. It's a 7A metal, so it has a -1, or 7A nonmetal, so it has a -1 charge in solution. So put simply, ionic compounds break up when they're dissolved in water. Potassium bromide is the same thing. Potassium is a 1A metal, so we get K with a +1 charge, which is aqueous, and bromide is a halogen, 7A, so it's -1, and it is aqueous as well. So both of these compounds break up in water into their ions. These ions allow electrical current to flow through the solution, so the solution is able to conduct electricity. It turns out that the more sodium ions and the more chloride ions, or the more potassium and bromide ions that you have in solution, the more easily electricity can flow through the solution. And it allows us to generate a relationship between conductivity and concentration. And if you took Gen Chem here, you did exactly this. So what we're going to do then is take some data where we actually make several solutions. You're going to make NaCl solutions. In this case, we have KBr concentration in our calibration curve in molarity. And you'll recall that molarity is moles of solute, in this case KBr, over liters of solution. So we're going to make these KBr solutions at different molarities. In this case, they range between about 0.01 molar, a little bit less than that, to around 0.05 molar right here. And we're going to measure the conductivity of these solutions using a MicroLab and a conductivity meter. As the concentration of the solution increases, so does the conductivity. We can then do a linear regression in Excel and get y equals mx plus b, the equation of this line. If we then measure the conductivity of an unknown solution, we can use this equation with a y value to solve for x and determine its concentration. So again, something that's relatively easy to measure, conductivity, you just stick in a conductivity probe, allows us to find something that's relatively hard to measure, which is concentration, using a calibration curve. One other thing I want to point out here is what is called the independent and the dependent variable. In this case, in this example, as well as in the example you're going to do in the lab, the independent variable is the concentration. So you're going to make these solutions of known molarities. You are then going to measure their conductivity, which is the dependent variable. So concentration is the independent variable and conductivity is the dependent variable. The independent variable is the one the experimenter controls, in this case concentration, and the dependent variable is the one that we measure, in this case conductivity. You'll also notice that the independent variable is on the x-axis and the dependent variable is on the y-axis, and this is traditionally how a calibration curve is generated. So now that we've talked a little bit about generally what a calibration curve is and what's going on with these ionic compounds when we dissolve them in solution, now we have to look into the specifics. So specifically in this experiment, you actually have to make sodium chloride solutions in order to measure their conductivity. And the first thing we ask you to do is to make 100 milliliters of a 0.25 molar NaCl solution starting from solid sodium chloride. And I'm not going to go over that example, but in a minute I'm going to go over an example, a similar example, where we're making a potassium bromide solution. You're then going to dilute your stock solution, in your case the 0.25 molar NaCl, to make a 0.016, a 0.012, a 0.008, a 0.004, and a 0.002 solution. So you're going to make 5 lower concentration solutions as described in the lab manual. In this case, we're just going to go over one example where we dilute our KBr solution. So what I want to do now is switch to the camera view so I can write. So I'll remind you that molarity, which is a unit of concentration and is abbreviated big M, is moles of solute divided by liters of solution. So this is the unit that we're doing. And in our case, we're tasked with making 500 milliliters of 0.300 molar KBr. In your example, what you're going to be doing is making 100 milliliters of 0.2500 molar NaCl. So they're similar, but they're not the exact same thing. So when I do these conversions, I use dimensional analysis, and when I do dimensional analysis, I like to start with a plan of attack. So in my case, I want to convert not from milliliters, but from liters, because molarity is moles per liter. So I want to convert from liters of KBr to moles of KBr, and then I want to take my moles of KBr and I want to divide it by my liters of solution. I want to go to moles of KBr, and then finally I want to go to grams of KBr. Got a little confused there what I was trying to accomplish here. So in this case, I want to go from liters of KBr to moles of KBr to grams of KBr. That way I'll know how many grams of KBr I want to measure out to make my 500 milliliters of a 0.3 molar solution. So in order to convert from liters to moles, we need to know the molarity. The molarity is 0.300 moles of KBr per 1 liter of solution. And we can write this as an equality. So 0.300 moles of KBr, the molarity number of moles, equals 1 liter of this KBr solution. We then need to have an equality between moles and grams. Well, the equality for moles and grams is the molar mass. And in this case, if you look this up on the periodic table, 1 mole of KBr is equal to 119.00 grams of KBr. So we add the molar mass of potassium and bromine. Now I could do this conversion. I've got my equalities, I've got my plan of attack. So I don't want to start with 500 milliliters, I want to convert that to liters, divide by 1,000. So 0.5000 liters of this KBr solution times. Now I want to put one thing on the equality on the top and one thing on the bottom that you may remember from general chemistry. In this case, I want liters of KBr to cancel out, so I put the 1 liter of KBr on the bottom and the 0.300 moles of KBr on the top. Times. Now I want to convert it to grams. Well, I want moles to cancel out, so I put moles on the bottom. I put 1 mole of KBr on the bottom and 119.00 grams of KBr on the top. When you took general chemistry, you may have thought you weren't going to use this dimensional analysis again, but it comes back over and over and over again. So if you haven't already learned how to do this, please take the time to figure this out, because you'll use it over and over and over again, and the quicker you learn it, the less time you'll spend doing these types of problems. When you do this math, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, you get 17.85 grams of KBr. So if I add 17.85 grams of KBr to a 500 milliliter volumetric flask and I fill to the calibration line, I will have made 500 milliliters of 0.300 molar KBr solution. This we're referring to as our stock solution. Remember that your job is to make 100 milliliters of a 0.25 molar NaCl solution as your stock solution. Now we want to dilute that stock solution. And in our example, we want to make 10.00 milliliters of 0.0480 molar KBr. In your case, the first solution you want to make is 25 milliliters of 0.016 molar NaCl. And you can look in your lab manual for the 4 other concentrations that you also need to make. But we're only going to do one example here. So our job is to take this 0.3 molar KBr solution that we made previously and turn it into 10 milliliters of 0.0480 molar KBr. And you may remember the dilution equation that we used all the time in general chemistry, which is C1V1 equals C2V2. In this case, C1 is our initial concentration, which in our case is 0.300 molar. The initial volume is how much of this 0.3 molar KBr solution we want to add. That's what we don't know. You could call it X. I'm going to leave it as V1. What are we trying to make? What's the final concentration we want to end up with? In our case, we want to make 0.0480 molar KBr solution. And how much do we want to make? We want to make 10.00 milliliters. Multiply the two numbers together and divide by the number next to the variable, and you find that V1 equals 1.60 milliliters. To actually make this solution, what we would do is we would use the volumetric pipette that was used in the previous section, pipette in 1.6 milliliters of the 0.3 molar KBr into a 10 milliliter volumetric flask. We would then fill that volumetric flask to the calibration line, and we would have 10 milliliters of a 0.0480 molar KBr solution. Remember again that in the lab, you're going to make 25 milliliters of a 0.016 molar NaCl solution as your first standard that you're going to measure the conductivity of. So this hopefully gives you a brief reminder of how to make the solutions that you need for the calibration curve and what a calibration curve is used for.
In a moment, I will show you how to use the MicroLab software in order to make your conductivity measurements. First, I just wanted to remind you that all of the math involved in making your dilutions can and should be done before you come to lab. This will save you time in lab when you're not having to do all that math, and you can just go and get the volumes of water and solutions and masses of salt that you know you need ahead of time. That way you can focus on doing the actual experiment instead of trying to spend a lot of time on the math. So, in order to make your conductivity measurements, you're going to be using MicroLab. MicroLab is a software system that you'll be using throughout the semester in order to make a lot of different measurements, but for this experiment we're going to be using it on the conductivity side. So, in order to use MicroLab, somewhere in your desktop, which does not look like this desktop, you'll find a MicroLab shortcut. It might say just MicroLab, or it might have MicroLab with a version number. Either way, double-click on the shortcut, and MicroLab will open. You should see this blue bar with the heading Reading from Flash Memory appear. That's how you know it's working. If you see that it says that the MicroLab is disconnected from the computer or not responding, the first thing to check is to make sure that the MicroLab is powered on, because if the MicroLab is not powered on, the actual box is not powered on, the software will not open. If it still doesn't work, then there are various troubleshooting steps that you could take with your TA in order to make sure it works. So, when you open the MicroLab software, you'll be greeted with this screen. Later on in the semester, we'll use some other functions here, but for now, we're going to click on this one right here that says MicroLab Experiment, and we're just going to double click it. Double clicking that will open up the default MicroLab screen. In this experiment, we're not going to use a lot of this screen. You can use it to make measurements at certain times, make graphs, or export your data to Excel. But in this case, we're just going to be using it for some simple things. Right now, I'm going to use it to show you the difference between measuring the conductivity of tap water and the conductivity of DI water, which is something you're expected to comment on and check during your experiment. So, in order to measure conductivity, you need to click this button here that says Add Sensor. When you do, another window will show up and it'll tell you to choose your sensor. In this case, we want to do conductivity, so unsurprisingly, we will click the conductivity option. Then a small red square will appear on what is a picture of the front of the MicroLab around the jack in which you must plug in the conductivity probe. It's labeled conductance, so it's easy to find. You must click inside of that red box, which will highlight it. Next, you'll choose your range of your measurements, either 0 to 20,000 or 0 to 2,000 microsiemens per centimeter. In this case, we're going to click 0 to 2,000 microsiemens per centimeter. Normally you would click Use Factory Calibration, but sometimes it won't work and you'll need to find the file yourself like that. So you'll just click Calibrate Sensor, read calibration from a file, and choose the appropriate file. In this case, I'm going to choose the low range 0 to 2000 microsiemens per centimeter. It'll open up a calibration curve and you can just click Finish. Now you're ready to make your measurements. You'll see here in the bottom corner that we have a conductivity reading, and currently there's a small number there because I have a wet conductivity probe that has a little bit of water still on it, so it's reading a very small conductivity. First, I'm going to stick it into the tap water to measure the conductivity. So I've fully submerged the conductivity probe. You can't see it, but it is fully submerged beyond the gold band, and you'll notice that the number is bouncing around. The number is around 138, but you'll see that the decimal points are changing pretty regularly. This will happen forever. If you wait for a perfectly solid number that sticks around for a long time, you will never ever succeed. So when you see a number like this where it says 138 and it bounces around a little bit, it's safe to just say that your reading is 138 and write that down for your measurement. We don't really need the 7 different sig figs that we have available to us. Now I'm shaking the water off it. I'm going to stick the probe into the DI water, and you'll notice in the DI water our conductivity is around 6. This makes sense because the DI water has removed the vast majority of the ions. You might expect a reading of 0, but in this case I'll leave it to you to figure out why the reading isn't quite exactly 0. So that's the basic idea on how to use the conductivity probe capabilities of MicroLab. Next, we're going to go over how to do the Excel spreadsheet for part 2 of the experiment. Now we're ready to look at our Excel spreadsheet and figure out how to use our data to create our calibration curve. First, I want to remind you of 2 things. One, again, you can have all of the math done for your dilutions and solution making done before you come to lab, and I strongly recommend that you do that because then you can find any errors or spend most of your time in lab working on the actual experiment. Secondly, I'll remind you that part 3 of the experiment requires that you use water that is approximately 60 degrees Celsius. It would be in your best interest while you're measuring your solutions from part 2 and working on making your calibration curve that you're heating the water at that time so that when you need it in a little while, it's available to you and you don't have to stand around waiting for water to heat up. This would be a good task for one of you or your partner to do while the other one is starting to work on the data itself. So you'll see here that I have a part 2 and 3 sheet on this Excel spreadsheet. This is the same spreadsheet that I used before to show you the data for part 1. Now I have parts 2 and 3 on a second sheet on the same Excel spreadsheet. This way I can save one file to the computer and my TA will have access to parts 1 and part 2 and 3 organized in a neat fashion. I've already gone ahead and entered in the conductivity of my DI and tap water that we just measured, as well as the conductivities and concentrations of the solutions that Colin and I are using with the potassium bromide solution, because again, we're using the KBR and not the NaCl that you'll be using in class. So, what we need to do is we need to create our calibration curve from this data. To do that, we want to do a few things. The first thing we want to do is highlight the data. That is simply done by clicking on the top leftmost cell and dragging down until all of the points are highlighted. Next, we want to go up to the top of the bar here and click Insert. We want to come into the Charts section of Excel. We want to find this little Insert Scatter or Bubble chart on the bottom in the middle. Click on it and you'll be given various options, and you want to choose the top left option, which is to insert a simple scatter plot. And your graph will appear. Now, you'll probably notice that this graph doesn't quite look like the graph that Colin showed you previously when he was going over a calibration curve. There's no labels, there's no line, there's no equations, so we need to add all of those things manually. The first thing we want to do is we want to add all the labels to the graph. So we want to come up over here to the quick layout section, and we're going to come down here to the bottom right, and we're going to choose that layout. Then I'm going to go ahead and get rid of this little bit over here, and doing that automatically adds our line of best fit, as well as displaying the equation of that line and the R squared for that line. If it wasn't there automatically, we'd have to right-click on our data points and choose Add Trend Line. Luckily, it's already here. So, next we need to add a title and labels to our axes. So in this case, we are measuring conductivity versus concentration. Then we need to label our two axes as conductivity, along with units, which I'm going to go ahead and copy from over here. And on our other axis, we have our concentration in molarity. So now we have a calibration curve made in its entirety. We have labeled axes with units, we have a title on our graph, we have a line of best fit along with its equation and the R squared value. If you don't have all of these different parts, you have not finished making your graph. Without any of those individual pieces, it's not clear to a reader, for instance, your TA, what the graph is trying to convey. Like I said before, it's really important that your data is easy to read so that your TA has no trouble grading it and giving you feedback on what you've done. Because again, you'll want to save this before you leave lab so that your TA can take a look at it and give you feedback before you submit your final report in a few weeks. One thing to look out for when you're looking at your calibration curve is this R squared value. The R squared value is a measurement of how well the trend line you've chosen to add fits your data. So in this case, we're adding a linear trend line to a set of data that we expect to be linear. Said another way, we expect that as the concentration doubles, the conductivity should also double. So when we look at this graph, we expect the R squared value to be close to 1 because we expect the data to be fairly linear. Generally speaking, in our course, when we're looking at our R squared values, the goal that we tend to set for ourselves is having an R squared of 0.99 or better. In this case, ours is 0.9998, so we've satisfied that. If, when you perform the experiment, you notice that your R squared value is below 0.99, it is possible in the moment to try to fix that. When that happens, it's usually because one of your data points is way off the line. So, for instance, this data point could be up a little higher or down a little lower, and it's usually pretty clear which data point is not on the line. If that happens, all you need to do is go back to your stock solution, remake that particular solution, and remeasure the value. This could fix your data and make your life much easier when you're writing your conclusion later. This is a reason that it's really important not to get rid of any of your solutions until you're fully completed with the experiment. If you took Gen Chem here, you'll know that we said that to you repeatedly then, and it's still true now, and it'll hold true through your entire scientific career, that you should never get rid of anything that might be useful in the future. So please make sure your data is good, and don't dispose of your solutions until you have confirmed that.
In part 3 of the experiment, you're going to take 5 milliliters of your stock NaCl solution, and you're going to dilute it into a 100 milliliter volumetric flask. But when you do this, you're not going to use room temperature water. You're going to use 2 different temperatures of water. You're going to use chilled water, which you could stick into an ice bath, and hot water from a hot plate. It's really important that you don't heat the water above 60 degrees. In fact, even if you heat the water a little bit less than 60 degrees, that's fine. We just don't want you to hurt yourself. If you're trying to pour in 80 degree water, that could cause burns. And 100 degree water, boiling water, could certainly cause burns. 60 degrees is hot, but it for us was manageable, and that's going to vary a little bit from person to person. So don't heat it up beyond a manageable temperature. What's important is you measure the temperature, and you can measure the temperature by adding a temperature probe to MicroLab or just sticking in a plain old thermometer so you can monitor the temperature. It's also important that you heat the water before you start this experiment. So while you're measuring the conductivity in part 2, as Tim said, you can go ahead and start to heat up your water. You can also go ahead and start to cool down your water. All you have to do is stick some water into an ice bath. So put water in a beaker, put the whole beaker in an ice bath, let it cool down. You're then going to take 5 milliliters of your solution, pipette it into a 100 milliliter volumetric flask, then fill the flask with either, in one case, hot water, 60 degrees C, and in one case, cold water, 8 degrees C. So you're going to add approximately 95 milliliters of each of these 2 temperatures of water to 2 separate flasks. Then, this is very important, you're going to allow those 2 flasks to come to room temperature. And we're going to look at the effect of volume on molarity. Now, molarity is moles of solute over liters of solution. When water is heated up, its volume gets larger. So at 60 degrees, when you pour 60 degrees Celsius water in there, the volume is going to be larger. When you allow that to cool down to room temperature, it's actually going to shrink. The volume of water will become less. Since the volume of water becomes less and volume's on the bottom, the concentration goes up. And exactly the opposite case with the 8 degrees Celsius water. When the water is 8 degrees Celsius, the water is actually going to have shrunk down a little bit. So when you fill it up and then allow it to warm up to room temperature, it should become slightly larger as it warms up. And in this case, we should expect the conductivity to go down. So the first thing I want to do is I want to find out what is the concentration of the final solution if I had have made it with room temperature water. Now in your case, it's going to be 5 milliliters of your stock NaCl solution, which is 0.250 molar. But in our case, we're going to use 1.25 milliliters of our stock solution, which is 0.3 molar kBr, and we're going to dilute it to a final volume of 50 milliliters. So these are going to be different numbers for you, but it's the same idea. Now if we use C1V1 equals C2V2, we can do this math. So first we want to take the initial concentration, multiply by the volume of that we use, and then divide by the final volume. So it should be 0.0075 molar solution if we had have used room temperature water. But in this case, we want to find out what is the experimental concentration of KBr. Remember how we talked about before, finding the experimental concentration is challenging, right? It's not a good way to directly measure it. Well, the way we can measure it is by conductivity. And we have 2 conductivity values here for the 60 degrees C and the 8 degrees Celsius water. And we have a calibration curve. So what we want to use is we want to use the equation of our line on the calibration curve to find the concentration of KBr. Remember that conductivity is a y value. So this conductivity is a y value. We want to solve for x. Remember to tell Excel to do math. We put in equals. We take our y value. We're going to have to put in parentheses because we have addition here, which is 413 in this case. And we want to add b because it's negative. So we want to add 1.1667, close parentheses. We then want to divide by the slope next to x, which in this case is 4 0.6858, and that will give us the concentration in molarity. We can then pull this down and do it again for the 8 degrees Celsius water. So we're going to warm some water, we're going to chill some water, we're going to dilute 5 milliliters of our solution, in your case, up to a total volume of 100, or 1.25, in our case, up to a volume of 50. You'll notice that when we use 60 degrees Celsius water, the concentration is high. This is because the water contracts as it cools to room temperature, and therefore we get a higher concentration. When we use 8 degrees Celsius water, the concentration is lower than we would have expected for room temperature water. This is because the water expands slightly as it warms to room temperature. So this shows that it's very important that we use a common temperature of water, in this case room temperature water, which is what we usually use because it's commonly available, in order to make all of our solutions. Now you'd have to really go out of your way to use 60 degree or 8 degree water to put it in an ice bath or to heat it up on a hot plate. However, we're here just demonstrating the concept and allowing you to use the concentration curve and interpret the data that you get from there. In the next section, Tim will talk about the outline that you are expected to hand in when you leave lab the first day, and some of it should be done before you come to lab.
So I'm going to discuss the report guidelines that can be found in your lab manuals. So you'll notice before the first experiment of each of the 4 sections in your lab manual that there is a section report guidelines. In this case, the section 1 report guidelines for experiments 1, 2, and 3. And in your lab manual, it won't look quite like this. It'll all be just black text. The color-coded version that you see here can be found in the description of this video and will be available in the description of each video for this course. So I want to take some time to discuss, 1, why we have this guideline and the outline, and 2, what this color coding means. So first of all, I want to talk about what you're expected to do for this course. You're going to hand in a few different things during each of the sections. For each report you do, you're going to hand in what we call an outline. The outline serves 2 purposes. 1, it gets you to organize your thoughts and put things together in a presentable manner for your TA. And 2, it gives your TA the opportunity to provide feedback on that data and information before you put it into your final report. The second thing you'll write on each experiment is, in fact, the final report. So, for instance, if we take section 1, you're going to write 3 outlines, 1 for experiment 1, 1 for experiment 2, 1 for experiment 3. You're going to receive feedback on each of those outlines, which you'll get 1 week after you perform those experiments. And then 1 week after you receive the last of your feedback will be when your report is due. So you'll have your outlines due in 3 consecutive weeks. Then you'll get outline 3 back, and then a week later, the report will be due for the first section. So now I want to talk about this color coding, because if you notice in this text, we have red, green, and blue text. The red text is work that you should do on your outline before you come to lab. That means that this title page, the introduction, the reactions, the materials and methods, the experiment stuff here, all of these things highlighted in red should be done before you come to class. You'll notice that not all of the introduction is color-coded red, and I'll talk about that in a second. In a second. But everything that is color-coded red should be done before you come to lab for experiment 1. Then if we scroll down, we find the green section. The green section is stuff that should be done during lab, but is still part of your outline. Generally speaking, it will be your results and brief discussions of your results, which you'll save to an Excel file on the T drive so that your TA has access to it and can give you feedback. But this will also be done during the lab period. Then, 1 week later, you'll receive feedback on both the red and green sections that you handed in. For the final report, which won't be due in the case of experiment 1 for several weeks, you will include the blue section. The blue sections on each of these videos will be the stuff that you're going to write after you perform the experiment. So you're going to have the red done before you perform the experiment, you're going to do the green the day that you are performing the experiment, and you'll do the blue after you have performed the experiment. The other color of text you'll see here is the black text. The black text is things that will also be included in the Section 1 report, but pertains to experiments we're not discussing at this time. So, for instance, right now, the black text is for things pertaining to experiments 2 and 3, but in the experiment 2 video, it'll be things pertaining to experiments 1 and 3, because we'll be concerned with experiment 2 at that time. So, just as a quick recap, red is the things you will do before you come to lab, green is the things you will do during lab, then you'll get feedback on the red and green, and you'll add the blue after you've performed the experiment to your final report to hand in to your TA. In the case of this video, you'll notice that almost everything, or even everything, in the red section was covered in this video. We've covered the very vast majority, if not all, of this red information so that you can include it in your outline and learn about it and find out what you don't know before you come to lab. The green section, also part of your outline, is the data that you'll work up during lab. And while it will be similar to the data we did in this video, as we pointed out several times, we intentionally used different numbers than you'll use during lab. But the same concepts hold true. And please remember, for things that say something along the lines of as well as reasons for why, that you include on your Excel sheet that brief sentence or two we discussed before explaining your data. This just lets you and your TA know moving forward exactly what's going on and that you both understand the data. So in the future, when you're watching these videos and you now know that all of this red text is covered ahead of time, you can actually read through the outline ahead of time and see which things that you're unsure of or which things you might have questions of, and be prepared to jot down some notes while we go over that in the video. Or, of course, you could just rewatch that part of the video a few times taking notes. It's also important to note that this entire video is fairly long. I haven't finished it yet, but the video is probably in excess of 35 minutes, and we understand that's a long time. So we recommend that what you can do is you can watch the video at 1.5 or even maybe 2 times speed to kind of get through the parts that you're more comfortable with and make it so that you can see all of the things that you want to see. It's also important to note that if you look below this video, we will have shortcuts to spots in the video where we cover parts 1, 2, and 3 specifically in case you know that you're going to need help with a specific portion of the experiment. All of that said, welcome to the course and good luck.